Hi everyone, I'm Muhammad Yousaf, the corresponding author of this manuscript. Manuscript ID is 2020 PSPC 0994 and the manuscript title is An Adaptive Grounding Scheme for Synchronous-based DG to prevent the generator damage and the protection malfunctioning during ground faults under different operating modes. Authored by Muhammad Yousaf, Amin, Jalilian, Kashem, Muttaqi and Sutanto from University of Wollongong, Australia. In the previous studies, different grounding strategy has been proposed and adopted for the safe and reliable operation of the synchronous-based DG. These studies also states the adverse impact of an inappropriate selection of the grounding impedance on the generator damage and the protection malfunctioning of the overcurrent protection devices. So the main aim of this research work is to design an adaptive grounding strategy for synchronous-based DG to suit any prevailing operating modes to improve the grid resilience. During the grid connected mode, a high impedance grounding strategy will be maintained to restrict the ground fault current passing through the generator winding to prevent any generator damage to the generator winding and core of the generator. And the maximum fault current contribution will be from the grid side for the steadfast operation of the overcurrent protection devices. During islanded mode of operation, when there will be no fault current contribution from the grid side, so this high impedance grounding configuration will be switched to low impedance grounding by a fast switching mechanism to ensure the fast operation of the overcurrent protection devices. In order to design the analytical model of the proposed adaptive grounding strategy, three different scenarios has been considered. In the first scenario, asynchronous-based DG is operating in the standalone mode, and the dissipation energy and the protection constraint has been designed accordingly. In the second scenario, asynchronous-based DG is operating in the grid connected mode and a high impedance grounding configuration has been designed for the synchronous-based DG. In the third mode of operation, a synchronous-based DG is operating in the islanded mode of operation and a low impedance grounding or adaptive grounding strategy has been designed, and the dissipation energy constraint and the protection constraint has been proposed for each operating scenario. In order to design an adaptive grounding scheme, we need a Icelandic detection scheme. So for Icelandic detection, the rate of change of excited voltage strategy was utilized along with the open close circuit breaker strategy to detect the Icelandic mode of operation. Upon the detection of the Icelandic mode of operation, the high impedance grounding strategy will be switched to low impedance grounding strategy by inserting a low impedance in parallel to the existing impedance by a fast operating switching mechanism by giving a control gate pulse on the switch of this, as can be seen in the schematic diagram. The complete description of this adaptive grounding strategy is defined by this flow chart. So the result shows the dissipated fault energy inside the generator winding varies due to the fault duration as well as the fault current magnitude. So dissipated fault energy increases linearly as the fault duration and also increases exponentially along with the fault current magnitude. So in order to restrict the fault energy dissipated inside the generator winding, we can use reduce the fault duration to restrict the fault energy dissipated inside the generator winding, or in the second way, we can either control the magnitude of the fault current and to maintain the low dissipated energy for fault energy inside the generator windings. So for the traditional grounding strategy for synchronous-based DG, which maintain a high low impedance grounding strategy during all operating modes. So we can see this proposed grounding strategy during the grid connected mode. This will maintain ensure the very low fault current magnitude during ground faults for the grid connected operating mode inside the generator winding. And this comparison can also be seen for the dissipated fault energy for the synchronous-based DG. So during if we keep the same traditional grounding scheme for all mode of operation, we can see it will will consume a lot of fault energy inside the generator winding, thus causing the generator damage as it was being used traditionally. But in the proposed hybrid grounding, the fault current magnitude will be restricted to a very low magnitude, as can be seen here, and this thus causing the reduction in the dissipated fault energy inside the generator winding, causing a very less damage or no damage to the generator winding and core. So during grid connected mode, the fault current contribution due to the fault current contribution from the grid and the generator causing the steadfast operation of the overcurrent protection devices. But during islanded mode of operation, we can see if we have not upgraded the grounding configuration of the synchronous-based DG, it may delay the tripping of the overcurrent protection devices, as can be seen by T2 or this curve. So in order by adopting the hybrid grounding during the islanded mode of operation, by maintaining a low impedance grounding during island mode of operation, this has increased the fault current magnitude being sensed by the overcurrent protection, thus the fast thus ensuring the fast operation of the overcurrent protection devices. And this figure also shows the active power output of the synchronous based DG during all the scenarios. So we can see if we don't upgrade the grounding strategy during islanded mode of operation, it will cause the fault current contribution from the generator for a very longer time, and due to the uh, delayed tripping of the overcurrent protection devices. So this scheme has been implemented on IEEE 30 bus test system. Two DGs were integrated as can be seen here. And for a fault at point F, the investigator two relays are 50 and the primary relay are 24 and the backup protection R50 has been investigated. So during grid connected mode, we can see the maximum fault contribution from the grid side and the minimum fault contribution from the DG side due to high impedance grounding, thus preventing the generator damage. And these two relays were operating in perfect coordination. And while during the islanded mode of operation, if we don't upgrade the grounding configuration of the synchronous based DG, so the some relays may not sense the fault due to the low magnitude of the fault current, and thus causing the delayed tripping of the some protection devices, which is a protection hazard for the reliable operation of the power network. So by maintaining by upgrading the grounding configuration during islanded mode of operation, the fault current magnitude is increased and thus causing the fast removal of the fault by the primary protection, also being sensed by the backup protection within the permissible CTI limits. So it will ensure the perfect protection coordination among the primary and the backup protection. So in this research work, an adaptive grounding strategy has been designed to prevent the generator damage and to prevent the protection malfunctioning during the islanded mode of operation. An autonomous switching control mechanism has been designed to upgrade the grounding configuration. And the future recommendation for the grounding configuration for the generator zone fault has been proposed for the safe decaying of the field current. Thank you very much.